Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the famous Riemann Hypothesis. Just as a quick recap, because it's been a month I think since our last video, we initially explored properties of the primes and we then arrived at the Euler product formula, the kind of golden bridge which connects the Riemann's zeta series with a infinite product over all primes. So there's a connection between the series and the primes. We then extended that series into the complex plane. This is something that Riemann did himself, and we explored what this function looked like. We wanted to explore its properties, as it were, and we've done that a little bit. We saw, whether it has, where it has zeros and where it has singularities. And we did find that when we extended the function from its original domain, which is to the right of real part 1, to the right of real part 0, we found what looked like zeros, and they all appeared to be on a vertical line with real part half. That is actually the famous Riemann hypothesis, that they all lie on that line, or the non-trivial zeros. Today we're going to just explore those zeros just a little bit further, and the main point of today's video is to introduce something called analytic continuation. We won't do it rigorously today. We will look at that in a separate video, in an appendix kind of video where we define it. But today we'll just kind of use it and develop an intuition for it, because that's I think is much more helpful. So let's dive in. So the famous Riemann hypothesis is about the zeros of the Riemann zeta function, and so a common strategy, unsurprisingly, is to explore the properties of the function's zeros. That's kind of a common approach to attack the hypothesis. So we'll dip our toes into doing that ourselves today. So previously we showed that this property here holds for the series, the first series that we explored, 1 over n to the s, the kind of the sum of those. Remember, that's valid for real part sigma more than 1, and this property was what we called almost symmetric, and it's saying that the function, when we look at it above and below the axis, the real axis, the magnitude above and below is the same, but the phase is inverted, so it's the complex conjugate, so it's almost symmetric. Do remind yourselves by looking at that video if you want to do that. But we're going to use this property a little bit more today. Now that was for the original series, which was for sigma more than 1. Now we could show, because remember we extended that series and we developed a new series which was valid for sigma more than 0 using the eta function. Again, go back and have a look at that if you need a refresher. Now we could show that this property also holds in this slightly expanded domain, sigma more than 0, and we could do the boring algebra to do that, and that would be perfectly fine, and we would show and prove that it is valid in this slightly larger domain for that new extended series. We could do that, but actually we're not today. We're going to do something different, a different approach, which is actually more powerful, and it's an excuse to introduce and explore analytic continuation, which is quite a powerful concept. Intuitively it's not difficult at all. There are some technicalities about it, but I think it's important today that we develop an intuition and then leave the technical stuff for next time when we define things a little bit more properly. People talk a lot about analytic continuation, and the books do as well, but it's often difficult to kind of pin down what it really is. So that's the aim really today, is to use this problem to explore analytic continuation. So let's talk a little bit hand wavy about what we might mean. I'm going to draw a picture first before we come back to this diagram. So imagine we have a 2D function, a normal function, with x and y. Now, if I've got a function that's defined between, say, a and b, and it's kind of like that, if I then have another function which is defined like this, and it goes over this one here, and then continues, and matches that precisely in between a and b. So the original one, let's call that f of x, and let's call this bigger one g of x. The question is, are they the same? Is g a more general version of f? And we saw this question before when we looked at the function 1 over 1 minus x. And we saw that, and actually z for the complex domain, and we saw that this is valid. Actually, let's stick to the real numbers, the simpler ones, 1 over 1 minus x. We know that this one is valid everywhere except at x equals 1, where it's there's a singularity, and we can plot that, and that's fine. If we write that as a Taylor series developed around 0, then actually the Taylor series is only valid between -1 up to +1, not including, so less than, not less than or equal to. So this is stuff we've done before, and we've already talked about how the Taylor series developed at x equals 0 is one representation of this more general function. And we also talked about developing the Taylor series elsewhere, say x equals 5, and then that would have a larger domain where it was valid, but it wouldn't cover the entire number line, and that too was a representation of this 1 over 1 minus x. So this is what we've done before. Again, go back and remind yourselves. So that's the idea of general functions and other functions that are representations of it in specific smaller domains. So here we've just repeated that idea, but the question is G always a generalization of f? And it would be nice if we could say yes. It would be nice if we could say that as long as they agree sufficiently, and we'll come back to what sufficient means, if they agree sufficiently, then they must be. It would be nice to say that. What do we mean by sufficiently? Well, just again to give you a quick intuition for when it might not be. Suppose I've got two functions which only agree at a and b, only at a and b. So f might be like this, and g might be like this. Now they do agree on a and b, but they're not the same. But if they agree at every point between a and b, you can see intuitively that it's easy to argue that they are the same. Well, with complex functions, it is easier to say when that is always true. And again, we'll leave the detailed explanation for next time. Let's go back to our 2D picture. So what we've got here in this dark patch is a domain A, and we've defined a complex function fz. Now this larger domain, which is bigger than but includes A, so B is bigger than A and includes all of A, we've got another function, complex function, G. And we would like to say that G, because it agrees absolutely perfectly on A, is in fact a generalization of F. Again, we're being slightly loose with definitions, but we want to develop the intuition. If we can do this, and if f and g are of a particular kind of function that behaves well, and we'll talk about what that is, then G is an analytic continuation of f. It's exactly what we did before with the the real functions in the real domain. So that's the idea. So I'm just trying to get the idea settled first. So G is a analytic continuation of f if it matches all over A and is exactly the same. That's the intuition. And in fact, we can extend the idea where if domain B doesn't actually completely encompass A, but overlaps it sufficiently. Again, we'll define sufficiently next time. But you can see that if in this area, this intersection, this overlap, the two functions agree absolutely, then you can see that, well, G is a continuation of f. They both represent some other higher function in smaller specific domains. So that's also analytic continuation. So that's the idea. Now, if you think about it, obviously there are going to be some conditions that need to be met, but we can kind of focus on those when we need to. Just wanted to get the intuition across first. So again, you can read this later yourselves by pressing pause on the video, but it just defines the specifics of those pictures. Actually, there's an interesting point here that f is not valid on the larger domain B. What we're saying here is this f isn't valid on all of B. Just like when we did the Taylor series expansions for 1 over 1 minus x, they're not valid outside their kind of domain of convergence. So f is not valid in all of B, it's only valid in A. So that's an important part of this picture we're describing. So that's analytic continuation in hand-wavy terms. And again, you can read this later, it describes that second part of that diagram. Again, it's interesting to know that we might know one function and we find the other one later, and if they agree over enough of a shared domain, then one is an analytic continuation of the other. In fact, the order doesn't matter. We might know G and find F, so F is a continuation of G. It depends which one you know first. It's also important to say that we're not going to explore recipes for finding G if we know F, or finding F if we know G. That's not what this idea is about. This idea is simply saying that if we happen to find G knowing F, then that is an analytic continuation. So I just wanted to clear that, because some people do say, well, this idea is great, but how do I find the analytic continuation? And that's a separate topic. Great. So let's think just a little bit about what those conditions might be. Clearly, not every function will kind of work with this intuition, but it turns out that complex functions which are analytic, they're well behaved enough to have only a single unique extension. Those have the behavior that we need, and in fact, if you study complex analysis, almost all of the exploration is with analytic functions, because they are not overly narrowly defined, so there are lots of them, but they have properties which are nice, and lucky for us, analytic functions allow this analytic continuation. Again, we'll defer the detail for the next video, where we'll kind of dig into it in a more kind of textbook-like fashion. So today's just about the intuition. So analytic functions, and that's the clue in the name, analytic continuation. So although we're going to kind of detail it next time, it's worth just kind of saying what is an analytic function. Well, historically there have been two ways of describing them. Some people will say that analytic functions are complex functions which can be complex differentiable, and you might already know that complex differentiability is actually quite a strong condition. So if that's something you know, that's great. If you know about complex differentiation, then if a complex function can be differentiated, complex differentiated, then it is analytic everywhere that is valid. The other approach is to say that analytic functions can be developed as Taylor series everywhere that they are analytic. So if there's a domain and everywhere in that domain the function can be described by a Taylor series, then it is analytic there. So there's two approaches. You can read about the history of maths to see which one came first or which one is more foundational, but they are actually equivalent, with one implying the other. Great. So let's use this analytic continuation with our exploration of the zeros of this Riemann zeta function. So you remember that property we had where we had zeta of s equals the complex conjugation of the zeta of the complex conjugation of s. We're going to use that to create a function f. And you might immediately spot why that's relevant to zeros, and if not, it'll become apparent. Now, whenever this function, zeta of s, the Riemann zeta function, is analytic, then so is this. That might be obvious to you, but we'll show that next time when we dive into analytic functions. So if this is if zeta of s is analytic, then so is f. So let's think about the an initial domain from which we're going to continue out of. Let's think about the real number line for sigma more than 1, where we know that the series is valid. Now on that line, fs is 0. Let's think about why. On the real line, that series of 1 over a real number, the n to the s series, if we feed that a real number, the output is a real number. And the same here, if the complex conjugate of a real number is a real number because it doesn't have any imaginary parts. So these two are the same, and therefore the result is 0. Let's draw a picture. So if I have the zeta of, say, 2, that, even if I don't write down the precise value, I know that is real, because it's the sum over 1 over n to the s, and n is just the integers and s is this real value. So and you can say 3 and 4 and 5, so the of x real is real for x more than 1. So that's why we can say that, which means that, let's use the word sigma. No, s is fine, yeah. We know that, and then if we look at, if s is real, then s bar is real, then the function of that, the zeta function of that is real, and the conjugate of that is also real. So the two are equivalent, so therefore that equals 0. So that's just writing it out in case it wasn't clear. So that's the domain that we are initially thinking about. We can call it domain A, and we want to expand out into domain B. So by using that analytic continuation idea, the principle of analytic continuation, if it's 0 there, it must be 0 in any domain where f is analytic and is connected to that domain A. Let's draw a picture. So we've got that familiar picture of A and B, and here we said A and B. This one just happens to be the real line sigma more than 1, and B contains A, and this one, that function, wherever it's analytic and includes and is connected to A, then this must also, it's an analytic continuation of that function here. So fs here is 0, and therefore it must be 0 here too, because it's a continuation of it. It's a generalization. So if this is 0 everywhere here, then it's 0 here. Now this picture is slightly misleading because this is a 2D picture, but actually on the complex plane, that first domain is just the line sigma more than 1, and then the extended domain is all of that more than 1. So it doesn't include that left hand side of that domain. So fs is 0 in the complex half plane for sigma more than 1. I hope that's clear. If it isn't, do comment and we'll kind of revisit this, because this is the crucial kind of step. Let's take it a bit further. It's also fs is 0 in the extended domain sigma more than 0, because we previously extended the zeta function to that larger domain where it also remains analytic, except at the pole s equals 1. So you can see this idea of repeated analytic continuations. So let's relate this to this picture. We had an initial domain A, extended it to B, and now we've got a bigger domain C which includes B, and it's going to be analytic here as well, and therefore f is 0 here, f is 0 here, and f is 0 here. So this is a neater diagram just showing that. So the initial domain was this real line greater than 1, and it's a sufficiently large domain, and which we can extend into domain B, which is the half complex plane greater than, with sigma greater than 1. It excludes that sigma equals 1. And then because we extended the Riemann zeta function from domain B to domain C, we've already done that, and it remains analytic there, except at this pole, then we can say that f, which depends on the Riemann zeta function on zeta, it's 0 here, it's 0 here, it's 0 here. So I've talked a lot about this. I've tried to take this in lots of small steps, just to really have this idea sink in. It is quite important, this idea, and that's why I tried to talk about it in words, in English, rather than too much mathematical definitions, so that we develop an intuition. Analytic continuation is used quite a lot, and it's important in the exploration of the Riemann zeta function, but this is a nice first example. So I hope that made sense. If it doesn't, we'll revisit it. Do comment. So let's see why this continuation was useful. So if that function that we constructed is 0, it means that zeta of s bar is the complex conjugate of zeta of s. It's how it was constructed. And that means this property holds in all of that extended domain. Let's say that again. That property holds initially on domain A because f is 0. F is 0 in domain B, so that property holds. And f is 0 in domain C, the bigger one, so that property holds. Remember, f is 0 is an expression of that property. F is 0 means this equals this. That's the property we were interested in. And this is where the power of analytic continuation comes in. If we later extend, if we're able to extend the Riemann zeta function even to the left of sigma equals 0, into the left hand of the complex plane, which we haven't done yet, if we're able to do that, then this property holds there as well. That's the power of this method. Isn't that amazing? So f is 0 here, f is 0 here, f is 0 here, and if we're able to analytically continue to the left, then that property will hold there as well. And that property talked about the almost symmetry of the Riemann zeta function, so it holds there as well. Let's not forget the exception, the exclusion of that pole, that singularity at s equals 1, where it's not analytic and therefore the property doesn't hold there. But that's okay, that's just one point. And you can see, because the complex plane is two-dimensional, the analytic process, continuation process, can go around singularities. So if there's one singularity here, we can go around it, which is great. And we couldn't do that in the real domain. Remember when we had singularities in the real domain and the Taylor series didn't extend beyond the singularity? That was the hard edge. There's no way of going around because the real number line isn't two-dimensional. Whereas in the complex plane, it is two-dimensional. If we've got a single point, which is a singularity, we can continue around it. So that's another nice property. So that's great. So how is this useful for us? We're supposed to be exploring the zeros. Well, if the Riemann zeta function is 0, then that property, which you've probably already guessed, tells us that the Riemann zeta function is 0 at the point that is the mirror image of S in the real line, the complex conjugate. So the zeros exist above and below the real line symmetrically. They are mirror reflections of each other. That was kind of obvious from that property anyway, and you might have spotted that early on, but if you didn't, that's okay. So let's just repeat that. That property tells us that if it's 0 at some s, it is also 0 at s bar. So the zeros exist in symmetric pairs at sigma plus it and sigma minus it, and if t is 0, then they exist on the real line. Now that is quite a nice insight. We already know there's no zeros to the right of sigma equals 1. We know that because we've already explored that question. We saw empirically what looked like zeros in the when we extended the function. Now, this property of analytic continuation tells us that wherever we can extend the Riemann zeta function, this property will hold. So wherever we can extend, let me repeat that, it's important. Wherever we can extend the Riemann zeta function analytically, then if there are zeros, they will exist in symmetric pairs. And that's quite a powerful statement. And for us as beginners, taking our first steps, that's quite amazing. We've used analytic continuation, a powerful technique to arrive at that conclusion. I think that's quite impressive. I think that's quite exciting. I hope you haven't been too bothered by the slightly wishy-washy discussion of analytic continuation. As I say, next time we'll do the detail, but I wanted to show what it was and how it works. Interestingly, the fact that the Riemann zeta function's zeros are symmetric above and below the real line is compatible with the Riemann hypothesis, which says that they all lie on the real line, up and down, the real part half. It's compatible with it, but it doesn't actually mean they all lie on a single line. Let's see what I mean by that. So if I've got my complex plane, and the Riemann hypothesis says that they all lie, the non-trivial zeros, we'll explain what that means later. So we saw them appearing, on what looked like the line real part half. Now, what we've just found is that the zeros exist at sigma plus and minus it above and below the real line, mirrored. So if there's one here, there's one at the same place below the real axis, and then another one there, and then another one there. So that seems to support the, well, that does support the Riemann hypothesis, but it doesn't prove it, because we could have zeros that are not there, maybe there, and maybe even here, and they are mirrored, which matches what we found, but they're not on this real line half. So to be clear, what we've proven is something that is compatible with the Riemann hypothesis, but doesn't actually prove it. It doesn't say that the zeros all lie on a single line, never mind the Holy Grail, which is a single line half. I hope that's been interesting. I hope that's been useful. Next time we'll dive into the more specific and precise definitions of analytic functions when analytic continuation applies, and we'll look at a few examples as well. I hope you enjoyed that. See you next time. Bye.